That's exam 4 for physics 201. Which of these is a measure of angular displacement? Okay, well, only radians, degrees, and revolutions are the proper units for displacement. Arcs is not. The answer is B. Excuse me. 1 revolution is the same as 2 pi radians. What is the angular velocity of the second hand of a clock? Well, the second hand of a clock goes to an angular displacement of 2 pi radians in 60 seconds, and that is approximately 0.1 radians per second. If the wheel turns with constant angular speed, then which of these things is true? A is actually the right answer. We'll go through these others. That is, the wheel turns through equal angles in equal times. That in a time t, it moves through an angle theta. It continues to move through that theta in intervals t. The angle through which the wheel turns in each second decreases as time goes on. That is not an answer. That would mean that it's slowing down, or this would mean that it's speeding up. So that's not an answer either. Each point on its rim moves with constant velocity. When I have this object that's moving around in a circular path, or when it's rotating, the velocity constantly changes direction. Or each point on its rim moves with constant acceleration. Likewise, the acceleration, which is towards the center of the wheel, is constantly changing direction. So E is not an answer. An object at rest begins to rotate with constant angular acceleration. If the object has an angular velocity omega in time t, what is this angular velocity omega in time half t? Well, I know that omega is proportional to t. That is, omega equals alpha t, so it's omega over 2 in half t. What point about in this bar that can rotate at points A, B, and C, which exhibits the greater moment of inertia? Right, that would be point A, because at point A, I have more mass located at larger radii. This figure shows configuration of particles on an equilateral triangle. Rotation axis is as shown here. And actually here, this should say 8 meters. I'll fix that. What is the moment of inertia for this configuration? Well, only these two particles contribute to the moment of inertia. They're 4 meters from the axis of rotation, both of them. So I is equal to 3 times 4 squared plus 3 times 4 squared. That's 48 plus 48, which is 96. Figure skater is rotating at 5 revolutions per second. Then she moves her arms in, so she's spinning faster. Which of these statements is true? Right, she hasn't increased her moment of inertia. She would have slowed down if she had increased her moment of inertia. She, in fact, has decreased her moment of inertia by a factor of 2. I know that I omega has to be constant, and I know that omega goes up by a factor of 2, so I has to go down by a factor of 2. All right, so that means these others are wrong as well. This figure shows 3 levers of the same length. List them in order of the force required. So in which of these requires the greatest force, and which requires the least force? All right, the greatest force is the one with the smallest moment arm, and then the next is this one, and then this one. So this will be the first one, this will be the second one, and this will be the third one. That's 2, 1, 3. So A is the right answer. Buckets are spinning horizontally and frictionless bearing. Suddenly it starts raining. Which of these statements is true? This is right. The bucket's angular speed will decrease because their moment of inertia is increasing. Remember, that's that I omega. If I increases, as the mass of the buckets increases, the moment of inertia increases, then omega decreases. Which of these basic SI units for torque? That's R times F. That's meters times newtons, which is kilograms meters per second squared. So it's kilograms meters squared per second squared. That's C. 2 spheres have the same mass. One is made of aluminum, the other is made of gold. Both are solid. Because gold is more dense, the radius of the gold sphere is smaller than the aluminum sphere. Which has the larger moment of inertia? The one with more mass at larger radii, which would be the gold sphere. All right, a hoop can rotate about its central point in any direction. The hoop has a radius of 2 meters and a mass of 30 kilograms and is initially at rest. Actually, this isn't exactly, not in any direction. I'll fix that for the test. This hoop just rotates about a central axis. So if I have a hoop, it rotates about this axis, and then I have a force that's applied at the top of the hoop. It has a that force is 12I plus 5J. So if I were to write, if I draw my XY coordinates right here, 12I, 5J, it'll look something like this. So that's my force, and it's acting on this hoop. Sorry, this should be hoop right here. At the top of the hoop, that is at a point x equals 0, y equal 2. So if I were to write the moment arm, it would equal to 0I plus 2J, right? Because my moment arm goes from here to here, and it's 0I plus 2J. And first I want to know, what is the torque? So torque is equal to R cross F. That is 0I plus 2J, or just 2J, times 12I plus 5J. All right, so I get 24J cross I plus 10J cross J, but J cross J is equal to 0, so I'll just leave it at that. And then J cross I, let's see, this is I, J, K. J cross I is equal to negative K, so it's negative 24K Newton meters. That is my torque. After 3 seconds, what is the kinetic energy of the sphere? So now that I know the torque, I'm just going to actually take the magnitude of the torque and leave off the direction. So I'll just consider the magnitude of the torque as 24 Newton meters. I need to find the moment of inertia so that I can find alpha, which is going to be torque over I. The moment of inertia, this is a hoop, 30 kilograms with a radius of 2 meters. So for a hoop, it's equal to mr squared. That's 30 kilograms times 2 meters squared. That's 120 kilogram meters squared. Then I can find my angular acceleration. That's 24 over 120. Let's see, 24 over 120. 24 goes into 125 times, so this is equal to 1/5 or 0.2 radians per second squared. So that's my alpha. I'm looking for the kinetic energy. Several steps here. So I know that my kinetic energy is 1/2 I omega squared. So my I've already found, it's 120. Now I need to find omega. I know that omega equals omega naught plus alpha t. I already have my alpha, it's 1/5. After 3 seconds, 1/5 radians per second squared, leaving this off as 0, times time, which is 3 seconds. So this is equal to 3/5 radians per second. And then I can find my kinetic energy, and that'll be the end of the question. 1/2 of 120 times 3/5 squared. 60 times 9 over 25. Let's see, I don't know what that is right off. It's 21.6 or 22 joules. That's the final answer. So several steps there. You had to find the torque, first of all, in the previous part, and then you had to find the angular acceleration, the moment of inertia, the velocity at 3 seconds, and then calculate the kinetic energy. So let's see, that question was worth 15 points. Yeah, so a man has a moment of inertia of 100 kilogram meters squared. He stands on a rotating platform and is initially at rest. Since the man has 1 kilogram mass attached to a rope of a length of 2 meters, he swings the mass on a rope at a rate of 1.2 revolutions per second in a clockwise direction. What is the magnitude of the man's angular speed when he swings the mass? So our initial situation is just the guy standing there. And in that case, his moment of inertia is equal to 0. In the final situation, it's the guy swinging this ball around. Okay, this ball has a certain angular momentum, L, and he is also going to have a certain angular momentum. I'll call this L of the ball and L of the guy. All right, these two angular momentums have to add up to equal 0. So I want to say L initial equals L final. That is 0 equals angular momentum of the ball plus angular momentum of the guy. Angular momentum of the guy is going to be his moment of inertia, which is 100, times his final speed. So that's going to be 100 times omega final. And for the ball is going to be the moment of inertia of the ball spinning around times its speed. Now the speed here is given, and the mass and the radius. I'm just going to treat this like a discrete particle. So that's going to be, the moment of inertia will be 1 kilogram times 2 meters squared times the speed, which is 1.2 revolutions. So first I have, I'm sorry, what was it? 1 kilogram, 2 meters squared. Times 1.2 revolutions per second. This is all equal to 0. And then I solve this for omega final. And that'll be the final speed of the guy. So then the ball will be going one direction, and he'll be going another direction. Let's see, that's 1 times 4 times 1.2. Sorry about that. 0 equals 4.8 plus 100 times omega f. And then my omega f will be negative 4.8 over 100, or negative 0.005 revolutions per second. So he doesn't turn around that quickly, but he certainly has a speed that he turns. So 0.05 revolutions per second. All right. Here's a basic kinematics problem. Propeller, an arm length starts from rest and begins to rotate counterclockwise with a constant angular acceleration of 2 radians per second squared. How long does it take for the propeller's angular speed to reach 8 radians per second? So omega naught equals 0 because it's at rest. It has an angular acceleration equal to 2 radians per second squared. And it reaches a final angular speed of 8 radians per second. I just want to know the time. Well, I know that omega equals omega naught plus alpha t. So t is equal to omega minus omega naught over alpha, which is 8 minus 0 over 2, or 4 seconds. How many revolutions does it take during that time for it to reach 8 radians per second? This, by the way, was straight from the homework. So that's 0 plus 1/2 of 2 radians per second squared times 4 seconds squared. That's an S right there. That's 1/2 of 2 is 1. 4 squared is 16 radians. Right, but it's asking for it in revolutions, so I say 2 pi radians, 1 revolution. This is equal to 8 over pi. 2.5. What is the linear speed at the tip of the propeller at 8 radians per second? Well, v is equal to omega r, 8 radians per second, times the length of that arm, which is 1.2 meters. That's 9.6, or I'll just say 10 meters per second. And what is the linear acceleration when it rotates at 8 radians per second? Well, the linear acceleration, a, is equal to 0 because it's not accelerating. But then what is the centripetal acceleration? That is a equals v squared over r, omega squared r, since I know what omega is, so that's going to be 8 radians per second, squared times r, which is 1.2, that's 64 times 1.2. 53 meters per second squared. Boy swings a 20 kilogram stone in a horizontal circle with a radius of 2 meters, and it breaks under 200 newtons of tension. What is the maximum speed the stone can have? All right, so as this thing goes around, there is a tension force acting on it, there's a certain tension, Ft, and that maximum tension is 200 newtons. If I say that the sum of the forces equals ma, that's Newton's second law, the sum of the forces is just that tension, and that's equal to the mass times the acceleration, which is v squared over r. So the sum of the forces, the maximum tension we can have is 200 newtons. The mass is 20 kilograms, that's the mass that is accelerating, v squared over r, which is 2 meters. All right, so now I solve for v. Which is 10 square root of 20. It's 4.5. That's in meters per second. All right, that's the speed. And then I also want to know what is that speed in radians per second. So I know that v equals omega r. A couple ways you could do this. First, v equals omega r. This is the easiest way. 4.5 meters per second equals omega times 2 meters. So omega equals 2.3 radians per second. Otherwise, you could say that the centripetal force Ft is m omega squared r, and then you could say that omega is equal to the square root of F over mr, square root of 200 newtons over 2 kilograms times 20 kilograms. Let's double check that's the same. 200 over 40. Yeah, 2 point. Well, you get a slightly different answer. 2.2 actually, but this just goes around. I'm just going to call it 2.3 radians per second. I think that was the last one. Yep. There's the multiple choice answers.